Welcome. So enjoy the snacks. I'm going to get us started. I get the honor today of introducing our speaker, Professor Amos Winter, who founded and leads the Global Engineering and Research Lab. And to be able to say a little more than that, I went back and I rediscovered this article. It was in MIT Technology Review 2008. The title was A Serendipitous Passion, combining two of my very favorite things, probably yours too, given that he chose that title. And it had this wonderful picture in it of Professor Winter operating a hand cycle. So he's in Tanzania, and he just looks as happy as can be. And he looks happy today too. Some things don't change. And the other things that don't change are, this article was all about finding a problem, right? Going into Tanzania, seeing how the wheelchairs weren't operating very well on that rugged terrain, doing some really high-level engineering to work on that problem, combining himself with a really strong team, working with another organization, often companies. In this case, it was Whirlwind Wheelchair Public Service Center. Yeah, okay. So that was like 2005, and you were making a transition between what? Working on fluid bearings and robo-clams, right? Fluidizing a bed. So these are also themes that don't change. Mechanical design, fluid dynamics. Some things do change, though. The Gear Lab, growing, what is it, 20 people now? I mean, it's something like that.
More.
And growing more. Yeah. And the involvement of industry in these problems is continuing and growing. I think the scale and ambition of the problems that are being addressed are growing, like the number of devices that are going to be manufactured and put in the field. Those are all improving over time, so it's really exciting. And so I'm really eager to hear the latest and greatest. Probably you are too, that's why you're here. So I should yield the floor now, Professor Amos Winter.
Thank you, Dan. Dan forgot to mention that he was very integral in that time of my life, as was Amy Smith, in doing that wheelchair work in developing countries, which very much influenced me to do what I do now. So thank you, everybody, for coming today, not only to see the premiere of the movie, but also to see this talk. And I'm excited to share with you what Gear Lab's been doing to really leverage engineering science, what we're really good at here at MIT, for global development. And the prevailing theme I want you to carry through this presentation is we're trying to do this very much by design, through a diligent process to identify problems, leverage what we're good at in engineering science to create innovations, and then really see the impact of these devices in the real world. So to start off, I want to just reflect for a moment, why run a research group that's trying to create products that are global by design? Well, I think it's interesting if you look at indicators of human health and well-being in particularly developing countries, and you can take, for example, the Sustainable Development Goals, you'll see all these metrics related to health, clean water, electricity, et cetera. But I suspect none of you personally faced any of these challenges today in your life. And I think what's interesting about that as an innovator is that solutions to these problems exist, but for some reason they haven't been transferred over to resource-constrained settings. And I think the reason is because of a price-performance mismatch. So if you take any family of technology, it's going to lie on a nonlinear price-performance curve. So if you take automobiles, you can pay a ton of money for a Ferrari that goes 70 miles per hour faster than your Toyota Corolla, but that's a little bit more performance for a lot more money. So the issue with technologies in development is that if you talk about a technology like clean water, nobody wants to drink semi-clean water, right? There's an element of performance that you just have to hit. But the problem is what people may be able to afford in resource-constrained settings might be much lower than what we pay for that solution up here. So it puts you in a situation that there's no way to adapt your way down this curve. You have to somehow think of a way to jump off it. And so in our group, we try to address this in three stages, in that we really try to understand the market-driven requirements around new technologies, and also the governing physics and mathematical relationships around the technology we might create. Then what we do is leverage what we're good at, right? Really math, physics-based engineering science, combine that with market insights to see solution paths towards disruptive innovations. And another theme I hope that comes out in this presentation is all of our innovations come from this combination of market plus technical. And then finally, what we're always looking for is not just a singular solution, but if we can grow a new family of solutions out of that and create a whole new product family and variants that can suit the needs of resource-constrained countries and wealthier markets at the same time. And the term for that process has been deemed reverse innovation. So another set of principles I want to just set down at the beginning is that we try to be very diligent in how we identify meritorious challenges to go after. So the first thing we always think about is, are we tackling a problem with merit? And what I mean by that is this a real compelling development challenge? You know, I don't want to be solving like a problem for a single village scale. Ideally, we're going after like billions of people scale. And we have to think about, is there an unmet economic opportunity around that, where maybe if we do a free market-driven solution, it can naturally scale and sustain because people are financially incentivized. And finally, it's important that we distill what are the metrics of performance that have to be met for a viable solution. So instead of saying, we need to just clean water, we can say, okay, the water's dirty with this contaminants, this is how much people pay for it, this is how much volume we need to produce, here's our energy source, et cetera, et cetera. Then the second lobe of this merit Venn diagram is we're always looking for problems that have true technical merit. So we have to ask ourselves, is it a real technology for development problem? Because if it's just a policy or funding for development, it's probably not in our wheelhouse. The second is we want to be confident that we can leverage our core expertise, technical insights, to create a solution. And then finally, you know, I run a research group. We have to make sure we produce knowledge out of this work as we create a solution that we can teach to the greater academic community. And I'm putting this up because this is where I see a lot of development projects go wrong, is that you may have people who have great boots on the ground knowledge, but may not be connected and really see the technical space. And then you often see, you know, brilliant innovations from deep technical insights where people create solutions that are not connected to problems. So you have to go between them. And then the final thing we're always thinking about is what I call value merit. And what I mean by this is we have to strike the right value propositions to all our stakeholders to make sure we can do a project and then ideally disseminate it. So we have to think about who's going to fund the work and what do they value. We have to think about who is going to be incentivized to disseminate this work and adopt it. And again, if you can have economic incentives for people to make and sustain a product, they make revenue out of it. And if people adopt it and they make money, there's a very clear connection there of why they'd adopt it. And so that comes back to who could make money around this. And so something I ask my students all the time is I think it's quite valuable for us to reflect on what is our own value proposition for why we do this work. There's, you know, you'll see people with different motivations in this space, but I think it's to reflect on, it's good to reflect on, do you want to impact lives? Do you want to make money, educate people, publish research, or maybe all of the above? So we are always striving to be at this intersection point of this Venn diagram. And so these kind of guiding principles have really set up the core tenets of what Gear Lab does. And so we're always addressing applied problems and focus on resource-constrained settings. We're trying to strive for humanitarian and economic impact, because we can scale very easily if we can tie it with economic impact. We're looking to make high-performance, low-cost global solutions. And really, engineering science is our core catalyst for innovation that we're always using. We want to advance knowledge out of our work, and we want to test our hardware in context. And so some quick snapshots of this type of process in the last few years is it's enabled us to fundamentally understand the mechanics of how to tune a prosthetic foot's stiffness and geometry to generate an able-bodied walking motion and make different prosthetic feet of different sizes and shapes for different weight individuals and populate different product lines of products for different market segments around the world. It's enabled us to do things like understand the fundamental physics of how you could make a different tractor architecture that generates lots of traction with very little device weight, and characterize the physical models of that and show how it beats draft animals in performance, and then actually validating that with real people who farm and hearing them say, yeah, this actually works, and that it works in a lot of different contexts. So those are quick snapshots, but I'm going to focus today really on our water-related work on desalination and irrigation technologies. And as I go through this, and I'll start with irrigation, you know, I hope you're reflecting on these three areas of merit that are coming out in these projects. So to start off with desalination, If you look around the world and you just randomly dig a well anywhere, you're more likely to hit brackish water. It's actually more prevalent than fresh water. And all the gray blotches on this plot show brackish water aquifers. And so people in those areas maybe could use that brackish water as a viable water source. Now, what compounds this even further is the colored regions show refugee areas and internally displaced people, as well as populations at risk of natural disaster. So you look at this map and there's literally billions of people who could maybe benefit from brackish water resources that are currently underutilized. Now, another element of this is that if you look at areas of water stress, so water depletion, that's another reason why you might want to utilize brackish water, because it's another water resource, but you want to use it judiciously. And then also, many of these communities are going to be resource constrained around the world and may not have reliable grid access. So you might be able to use solar as a power source. And it tends to be that you have high solar irradiance in hot, dry areas where you may want to desalinate. So what we did is kind of put that narrative together to try to see what would be a viable desalination solution for resource-constrained settings for brackish water desalination. And the two candidate architectures would be reverse osmosis, which is the industry standard, and also electrodialysis, which has been around for 60 years and is also a commercially viable product. And so what came out of this work was realizing that for brackish water salinities, which are usually around 2,000 or so, and for situations where you want to best utilize that water source, where you want to maximize your drinkable water versus your input water, electrodialysis is always energetically favorable. So to put that in context, for like 1,500 milligrams per liter, the specific energy of electrodialysis is about half that of RO. So what that means is if you want to go off the grid, it cuts your power system cost in half. Furthermore, if you're in a water-stressed place and you want to really judiciously use that brackish water source, you want to minimize wastage. And current small-scale RO systems waste usually around 60% of water that comes into them. In ED, waste around 10%. So you put together this whole detective case, and if you want to do inland brackish water desalination and do it solar powered, and by the way, this is a grand challenge in desalination of how do you do renewable power desalination without tons of batteries? And oh, by the way, more than half the world's population lives more than 100 kilometers from the coast, right? So they can't use seawater desalination. And if you want to do that with high recovery at low cost, PVED, photovoltaic electrodialysis, is what we found is the best and most viable solution to hit those metrics. So we started this work a number of years ago. This was our first kind of village scale system that we made, and we won the USA Desal Prize with it. And then we've gone on to do pilots in many different places around the world. And what has been the real guiding light in what's driving this research is how do we make this technology cheaper? So to put that in perspective, our first prototype was over 60 grand, most of that in the unit that's taking the salt out, the electrodialysis stack. And in contrast, just an off-the-shelf RO system that could serve a community is an order of magnitude cheaper. So how do we make this a lot cheaper is what we'll get to. So before that, I want to instill some insights into how ED behaves and then how we leverage that to our advantage. So this is showing an electrodialysis stack, which is composed of ion exchange membranes. And what you do is flow water between the membranes, and the membranes can pass either positive or negative ions. And as you apply a voltage across this stack, the ions will travel through at most one membrane of the opposite charge until it gets blocked by the next membrane of the same charge. So what you end up with is alternating channels of your diluent, which is your product water, and your concentrated brine. Now, the other principle that's important here is that as you apply this voltage across the membrane, you're going to drive a current. And that current is going to be spread out over an area, which is, and this is called the current density. And this is an important metric because if you exceed a current density, you'll start splitting water molecules rather than transferring salt ions, which is not productive and also can be damaging for the system. So what we did was really understand this whole process at first principles and be able to extract how could we make this work well with an intermittent power source like solar. So that came down to first understanding the system's going to have a flow rate. The water's going to have a certain salt concentration. We can calculate our limiting current density as a function of concentration and flow rate. We always apply a safety factor on current density because we don't want to hit limiting, so kappa is that safety factor. We know that our pumping power is actually a very sensitive variable, that if we tweak our flow rate a little bit, it changes our power consumption quite drastically, as is our electrical consumption of power from the current density going through the stack. And so what we realized is that if we wanted to match our total consumed power of the system, which is driven by the pump and the stack, to solar power, we've got two very sensitive knobs to turn. So we can vary flow rate and vary current density to maximize our production rate at any power level. And there's a distinct, unique solution to this at any input power level. So to put in contrast like why this is valuable, this is how you typically run a solar-powered ED system before our work. So you'd have a solar array, you'd capture energy in the middle of the day, you'd store it in batteries, and then you run batches, shown in these sawtooth patterns, and you use the battery in the beginning and end of the day to maximize your production. So with this time-variant ED behavior, what we can do is constantly vary our pump power and our stack power to track the irradiance curve throughout the day. Even if it's clouds go by, doesn't matter, we can track it. So we match our consumed power with available power, and we can produce the same amount of water without any batteries at all. So I want to give a shout out to John Bassett and Shane Pratt, who came up with an extremely elegant controller of how we actually do this, where what we do is we're always looking at how much power is coming into the panels, and if there's a little bit more power available, we'll uptick our flow rate a little bit. That will increase our limiting current density, and we can uptick the current a little bit. And so if we can iterate this really, really quickly, we can always converge on our consumed power with the solar power very, very quickly, and we can do it without a full predictive model of the system. This was an Achilles heel for us early in this work, where we tried to model the hydraulics circuit and electrical circuit fully of the system, and it was computationally unwieldy to solve those coupled equations. But this is really dumb simple and really fast. And so it relies only on a single closed form calculation of current density based on flow and concentration. So we can do that really quickly. The faster the duty cycle we need, the less energy buffering. And we always need a little bit of energy buffering now because there's transient response lags in the system as you change the current density and as the concentration changes as it flows down the system or as pumps turn on and off. And then we don't need any battery storage for this. We need a little battery buffering, but no actual storage. And there's no scaling limits on this. We can make big scale or small scale systems. So over the last few years, we've piloted successive versions of this idea of time variant ED, leading up to the last two pilots we did in 2019 and 2022, which really showed the merits of what this technology can do. So the first in 2019 showed that we can hit price parity with on-grid reverse osmosis, the existing standard. So this is showing the breakdown of levelized cost of water, which is cost per volume produced over a 10-year amortization timeline. This is the kind of standard that you'd find in villages of India. We took our partners' small-scale RO systems that they've installed over 3,000 of throughout India as the benchmark, and we were able to hit price parity or maybe even lower with our time variant systems. And what's particularly exciting about this is that's inclusive of the capital cost of the solar system. So yes, our capital cost is higher, but we very much make up for it in the low recurring cost. And then most recently, at the end of last year, we did a 4-month trial with our newest version of the controller. And this is showing our extracted power off the solar panels, our used power that we actually utilized, what the discharge and charge is of the battery, and then the power breakdown between the pumps and the ED stack and the rest of the system, and then also water production throughout the day. And so the real highlights of this is that we were able to utilize 91% of the solar energy coming off the panels to make water without running it through batteries, right? So almost all that energy hitting it is making water. We also dropped the battery capacity almost to zero. So this system, which runs at 1.6 kilowatts, was using a single 120 watt hour DeWalt drill battery as the only battery buffer, right? So essentially no battery storage in the whole thing. So to put this in perspective, this is a bunch of solar, all the solar desal systems we've been able to find in the literature that are RO-based, ED-based, and then this is our flow command current control, newest version of our controller. And what really drives this home is your battery capacity needed versus power of the system. And so here's the median value up here, and we are 3 orders of magnitude lower than anything else out there. So again, given that desalination with renewables and without battery storage is such a grand challenge, this is super exciting that we're doing it. So we are very aggressively pursuing a number of tech transfer opportunities to really scale the impact of this in multiple applications. So we're currently actually forming a company around all this technology, and probably our bread and butter market is going to be small water enterprises, but we're also seeing a lot of opportunity in irrigation. So to highlight that, we did a case study, or a feasibility study rather, in Jordan a couple of years ago, another water-stressed ag area. And we interacted with many stakeholders, and the consensus that came out of that is, one, farmers are very sensitive to energy costs. They would like to use solar so they don't pay for grid electricity, and that ponds are readily available on most farms. And why that's valuable to us is that if we ran a conventional constant power ED system, we'd be limited to the power we could run that we could fit under the bell curve of the solar irradiance. So that would limit our water production. If we can track the whole solar irradiance curve, we can make a lot more water, fully utilize that energy. But the other unique thing about this is that this architecture would be producing water faster in the middle of the day at high power than at the beginning and end, and that actually changes the product salinity you make. It gets a little saltier in the middle of the day, but when you have a pond, it doesn't matter. You can just dump it in the pond, average it out, and use your water from there. And so the big take home that came from this study is that compared to the industry standard right now, we can make water 24 to 40% cheaper for agriculture applications. And this has led to a large USAID grant that we're continuing on now, and we'll pilot this in Egypt in the next couple of years. We also do home scale systems and work with the market leader in India, Eureka Forbes, that makes these, as well as the Middle East Desalination Research Center. And this is another example of the parametric insights helping us, that we realized if we make a small ED stack, we can get away with 1 feed pump instead of 2, which you usually use, and that has cost and packaging ramifications. And then we're also looking at disaster response, humanitarian response, and full-scale municipal systems. So in the next year, we will be piloting home-scale variants in the Navajo Nation in the American Southwest, as well as setting up what would be a characteristic scaled-down municipal version for Texas, which we think is going to be a beachhead market because they want renewable desal because they're sensitive to their grid going down from weather variations, and they want to triple their water production in the next 70 years. So this technology is quite aligned to that. So moving on into irrigation, again, I want you to be thinking about this Venn diagram of merits, and hopefully that shows through. And so to start off, the reason we care about irrigation is agriculture is the biggest employer in the world, right? And there's literally 500 million like small scale farms that if they can irrigate and grow more crops, they can make more money, get out of poverty. So irrigation is actually the most impactful development intervention in international development. The challenge is, if you want to take hundreds of millions of farmers who are not irrigating now and make them irrigate, it can lead to a lot more water stress. So right now, this is showing the breakdown of the average of how much water is used for agriculture throughout the world, and it's 70%. And why this is so important is this is showing water stress throughout the world. So if you look at countries like India and many parts of Africa, we can't afford to just extract lots more water out of the ground because it just isn't there. So how do we irrigate effectively with less water? Drip irrigation is a nice way to do it. So these are drip lines in a field, and drip irrigation can cut your water usage by upwards of 60% compared to traditional flood irrigation. However, it only accounts for less than 1% of the global irrigation market right now. So cost and complexity are barriers for increasing that adoption that can lead to irrigation, but less water withdrawal. Now, what further compounds all this is that throughout the developing world, it's very common to see diesel-powered water pumps. Those have been kind of the backbone of adoption of irrigation. Problem is, agriculture already accounts for 24% of greenhouse gas emissions. So we don't want to increase a lot of diesel power use. And again, solar would be great to use. However, it also has very low market penetration. So even in a wealthy country like the US, less than 7% of farms use solar. So all of this has driven us to look at, how can we find low cost, low power, powered by renewable solutions that save water and would be adoptable and reliably operated in low resource settings with local labor. So to sum that all up, what we're trying to do is precision agriculture in historically non-precision environments. So let me tell you about how we've done that in a bunch of ways. So the first area of work is on ultra low pressure, low cost drip emitters. And so this is a schematic of a solar powered drip system where you have the panels, pump, and field. And then if you look in the field, you'd lay down lines of drip emitters that correspond to the placement of your crops. And inside these pipes are these little flow regulating devices. This is the drip emitter. And so why we care about these is that if you look at what consumes the pressure in the system, most of it is from the emitters because you need to apply a certain pressure on these to get a desired flow rate. And so if we can somehow cut the pressure required to make these operate at the correct flow rate, we can cut pumping energy and directly cut the cost of a solar irrigation system. Now, we're also concerned about the actual material costs of these things. So here is the lifetime cost breakdown of the hardware of a drip system, and the big driver of that is the emitters and piping, and most of that is the emitters. So the second objective we're always thinking about is, can we drive down cost by just driving down the emitter size and using less plastic? So the way we've done this is, again, diving into first principles. How do these things work? So here's a schematic of the emitter. Water flows in the inlet here, and here's the emitter bonded in the pipe. But water flows in, the pressurized water acts on a deformable silicone membrane, and then it gets diverted through a tortuous path. That tortuous path causes an additional pressure loss in the flow. Then the water flows up underneath the emitter, so now it's coming in at an even lower pressure, which creates a higher pressure differential on the membrane that forces it down, and it flows around the lands and up through a little channel, which you can see here, hopefully with the light, but it's a little channel that when the membrane is depressed down, guides all the water through that little channel. So as you add more and more pressure to the system, it forces the membrane down more and more and increases the resistance here. And so this is a pretty complicated little flow control device in that we have a turbulent labyrinth here and then a coupled fluid-solid interaction device in the membrane's interaction with the lands in the channel. And a variable, essentially, channel length as the emitter gets pressurized more and lays down more. One kind of historical interesting aside is this flow restrictor device was invented in the 1940s and was popularized for irrigation in Israel in the 70s. And up until our work on this, as far as we can tell, these systems were always designed empirically, kind of guess and check. And so we have been the first ones to really understand the governing engineering theory of why they behave the way they do. So we've done that through this kind of succession of breaking down this more complex design into the coupled solid and fluid interactions. So really understanding the deflection of the membrane as a function of flow rate and this variable flow circuit where we have a varying resistance as the membrane contacts the channel, but then we also have the labyrinth resistance and other minor losses. And I want to give a shout out to Aditya Godunkar, who has been the driver of creating this awesome technology that you're going to see. So we were able to break this down to its governing behavior of what, how this delta pressure on the membrane affects deflection, how that pressure load on the membrane is dictated by flow rate, and then also the pressure loss through the channel is affected by flow rate and FRE, flow resistance, depending on Reynolds number. So We can plug that into an iterative solver because we've characterized all this analytically. And this works by applying a starting pressure, guessing a diaphragm deflection, putting that into a coupled numerical solver to iteratively calculate flow rate, resulting deflection, et cetera, converging that, and then getting an operating point of pressure and flow rate out of the emitter, plugging that membrane deflection in at the next pressure, et cetera. So what comes out of that is a fully predictive model of the pressure flow rate behavior. And so I'm showing here in gray a commercial emitter and then one of ours in blue. And these are actually experimental results, but we simulate this as well. So what I want you to appreciate here is that we're starting our emitter's designated flow rate at 1 liter per hour at 70% lower starting pressure than the commercial products. What that translates to is about a 50% reduction in pumping power that you need back at your pump house. So if you're a farmer on the grid, cuts your energy costs in half. But to put that in another way, if you look at the lifetime costs of the whole system, this is for a case study in Morocco growing tomatoes. It would cut farmers' cost of the whole lifetime system cost by 21%, just going to this lower operating pressure, and for solar powered by 24%. And what compounds this even further is that many water-stressed countries are providing subsidies for water-saving agriculture technologies like drip irrigation. So even if they get that subsidized and the farmer has to pay for the pump and power system out of pocket, it cuts that cost by 58%. And again, this is not changing any usage practice or anything like that. You just plug in these emitters rather than conventional emitters and you get these big power savings. The other thing Aditya looked at is how to reduce the size of the emitter. And so he did that in a really clever way by looking at all the geometric factors that govern the behavior of this tortuous path, which is a more complicated turbulent flow that we actually have to simulate with CFD. So there's a number of these geometric factors, but you can actually reduce the most sensitive ones by accounting for manufacturing considerations, symmetry, redundancy, and constraints, to boil that down to only 3 factors that will affect your flow resistance K independent of the length of the emitter's path. So why that's important is that we can choose a very short length to make a smaller emitter and just choose the tip distance, the depth of the path, and how many units to get the right flow resistance. What that's manifested in is a new design that we've developed with Toro, which is one of the industry leaders in drip irrigation. So here's our design versus Toro's existing design. This has tons of compounding benefits. So first, ours is 58% shorter and uses less than 50% of the material as Toro's current product. So to put that in perspective, these are commodity products, right? Toro gets a sliver of margin off each one of these they sell, and we're cutting the material cost in half. So they are tickled pink about this and are very aggressively pushing to commercialize these. By cutting out this material, we can also reduce the cost of drip tubing by 20% and an overall system by about 10%. And then the final thing that's really exciting and has attracted USAID to support this work going forward is that we can make these at a central location under high precision conditions and package them into a container and ship them around the world to embed into drip lines. And the reason you do that is you want to ship long distances a high density product, a bunch of these in a box, but then when you make tubing, it's a low density product because it's mostly air. This has changed Toro's whole outlook on global dissemination of this. So now we can make these emitters, likely in Southern California, ship them to the Middle East or North Africa, embed them in lines, and people can use them everywhere. So it's pretty cool that this one tweak of the geometry changes the whole global economic model. And I brought some of these. Please don't steal them after the seminar, but you can see these side by side, the differences. Great. So we haven't just looked at the design of the emitters. We also realized that there is a lot of meat on the bone for how to improve the design of the overall system. So the way we did that was starting by looking at an overview of how the system works and the interconnectivity of all the elements in a solar-powered drip system. And all this controller work you're going to hear about in the next few slides. I got to give a shout out to Carolyn Sheeline and Fiona Grant who have led the efforts on all this. So what's happening in the system is you've got the sun, which is driving evapotranspiration. That's the loss of water from the plants. those plants need to have that water replenished, so that creates the hydraulic demand. That dictates how much water the pump has to provide. That dictates your power and energy demands, which are satisfied by your solar panels, that energy comes from the sun. So there's this whole interconnectivity between all these elements. And one of the tricks that Carolyn and Fiona figured out is that you typically design a solar irrigation system to have some amount of battery capacity, where if you have a farm, this is a farm showing 3 sections of the farm that you'd want to irrigate throughout the day. What you do is charge your battery in the middle of the day and then use that energy in the beginning and end of the day to be able to run all your sections and meet your irrigation demand at the end of the day. And so what they figured out, which is a nice trick to save capital costs on batteries, is doing what we call load scheduling. So we can figure out the duration of each section of the farm we want to run so it can fit under the irradiance curve. And we can actually change our pump's operating point to run 1 section at the beginning of the day and then 2 sections in the middle of the day and get rid of our batteries. So this approach and this kind of integrated view of the whole system has many, many, many benefits. So as far as we know, and this is definitely affirmed by Toro as well, this is the first end-to-end solar power, hydraulic, and crop performance model that is all integrated together and enables you to design and optimize full irrigation systems. We're seeing that we can cut the power system costs by 30% compared to commercial solar irrigation products. We need almost no battery storage by doing this, and we can actually increase water delivery reliability by 27% versus current on-the-market solar irrigation products. So many, many compounding benefits. So that's a system design architecture that I just talked about. We also had to figure out, how do we control this thing in real time, particularly with such a varying power source like solar power. And so this is a schematic of our predictive optimal water and energy irrigation controller, or power controller. And so the way this works is we use a very low-cost weather station. This is a $100 weather station and a cell phone modem to send information up to the cloud. All the complicated irrigation scheduling computing and figuring out when to run different sections of the field is done up in the cloud, so you need very little infrastructure on the farm. That is then sent down to the phone of the farmer on the field, which is typical that you'll find in developing countries. You know, even if there's a wealthier owner, you'll probably have a farmhand who's working the field. And then that farmhand can manually turn on and off valves to do this precision agriculture technique. Or for bigger farms, you might want to have automated valves, which is also common. So the benefits of this is that, you know, we're trying to increase crop productivity and reduce costs without sacrificing reliability. And we're doing that by doing an optimal irrigation schedule every day that's minimizing water, minimizing energy, but maximizing crop growth. We're reducing risk because we're doing predictive models in the future and tracking what's happening with the crops so we can reduce stress. And there's a bunch of tricks in here to lower hardware cost, in that the expensive computing power is up in the cloud. We need minimal batteries, like I talked about before. We're using a $100 sensor where you'd usually use a $1,000 weather station to do this type of precision ag. And we can put a human in the loop if we want, or take them out of the loop and do it fully automated. So a cool aside to all this tech development is that what happened concurrently in this project is Georgia Van de Zandt, who is a recent graduate of our department, was figuring out what would be the usage practices that people would adopt, and would they actually value the performance of this system. And so these are some pictures of Georgia and Fiona going through storyboards showing the operation protocol of getting cell phone commands, closing valves, opening valves, et cetera. And also this is showing at a high level how the controller works. And so what was so powerful about this is that we were able to affirm that people wanted this and could adopt it before the technology actually existed. So it made us much more confident that this could actually work in real life and people could operate this effectively. This is showing the full schematic of the control system of the irrigation controller, and it's a 3-level system. And I'm going to go more into level 3 in the next slide. But what's happening is this is what takes place up in the cloud of predicting an ideal irrigation schedule based on weather inputs. And then what happens in real time is the system's always tracking the current weather, how much power it's getting, and it's always trying to minimize the charge rate in and out of the battery to reduce the degradation of the battery, and always trying to use the battery energy, though, to accomplish the irrigation schedule that was set out at the beginning of the day. And then the final level, level 1, is controlling the pump. And why that's important is that we have to run the pump at different operating states at higher and power lower levels. And then we also are tracking if there's any degradation in the system, like filters clogging, so we can still deliver the right flow rate of water even as the resistance in the system changes. So to walk you through what the level 3 controller does, we start with this very low-cost weather station, the $100 weather station, and then we'll take historical data from a nearby region where there's a long-established weather station. So we take that data together, we put it into a solar model, which predicts how much power electrically we can get out of our panels, and a weather model, which predicts how much rainfall we'd expect the next day, and how much evapotranspiration, which is the water loss of the crops, we would predict in the future. Then what happens is that goes into a prediction model, and so we use that measured data and the historical trends using machine learning. We then predict what we expect tomorrow for the predicted available solar power and the predicted weather, both in terms of rainfall and evapotranspiration. That then goes into a soil moisture model, because what's happening is every day the crops are losing water from evapotranspiration and maybe gaining water from rain, and we have to look at that balance to see how much water do we need to add without overwatering and using more water than we need to. So this predicts the irrigation demand by the plants, and then that goes into an irrigation optimization, which is optimizing both the water delivery to minimize water use but maximize crop productivity, but also do it using the power available. And as far as we don't know of another coupled power and agronomy irrigation controller that does this. And so what happens in this optimization is it's actually forecasting day by day what the irradiance will look like. This would be like a lower level day, and then stacking the different sections of the field every day to get the irrigation events that are needed to keep the irrigation level at where the crops want. So the real key behind this optimization is this cost function that Carolyn and Fiona developed together. So what's going into this is that we're trying to minimize risk by always charging the battery if we have a battery in the system, so we can irrigate if a cloud goes by. We're looking at the yield projection at the end of each day because we want to maximize our revenue by yield production. And then we're also looking at how to minimize both water use and charge rate in and out of the battery to minimize degradation of the battery. And then what happens is that as the system runs on this prediction, it's also tracking what's happening in real time. And by the way, I forgot to mention that it will send this schedule down to the farmers, so they'll know the game plan for the future. But then as the system runs, it's tracking the actual solar radiance and the actual weather, and it's also tracking what the farmer does. So if the farmer forgets to turn on a valve or turn off a valve, it knows. And it knows if the plants have lost water. So it looks at the actual irrigation delivered and sends that back to the soil moisture model. It measures the actual weather for this current day and how much evapotranspiration and rainfall did you have, right? And then it gets a much more accurate prediction for the future of what the water demands are going to be for the next day. This feedback loop is the most clever part of Carolyn and Fiona's controller, because what it's doing is it's accounting for every error, and day by day, even if there's a big error in weather or usage practice, it can compensate for it while still minimizing water usage. So to test this out, we've been running this for the last few months, this controller in different farm settings in Morocco, Jordan, and Kenya. And the Morocco farm is a larger farm that's fully automated, so the valves are automatically switched, where the Jordan farm is actually manually operated valves. So we're testing the two conditions of farmer in the loop that I talked about further. And so this is the main highlight that we've seen so far in this controller. So this is a full season of irrigation for a potato crop in Morocco, where we showed we reduced water consumption by 44% and energy consumption by 38%. And just to let that sink in, right, these are drip systems, and a drip system already reduces your water consumption versus flood by about upwards of 60%. We've cut that by another 44%, right, and had this operate properly, where it's producing a negligible yield difference. We were 9% lower in our farm operating the controller, but we'd expect upwards of a 20% difference because of water quality differences. So effectively, these are on par for yield productions. So again, cutting water, cutting energy versus a conventional solar drip irrigation system, and still getting similar yield. And same story for Jordan, where we have a farmer in the loop. We corrected an error after a couple months, and then we've seen, again, 31% savings in water, 32% savings in energy, and we have no yield difference in okra on this farm. So we are super excited about this. And so USAID has made a big investment to help pilot this on a much larger scale, and that will actually transition into a company over the next few years built around this power controller. So super, super valuable tech. So to wrap up, I just want to reflect for a second on, I hope you saw through this that we've tried to be very intentional and diligent about addressing these three areas of merit in all of these projects. And I think this has been the guiding light that has enabled us to evolve these technologies over a long time, generate a lot of investment, and makes us very confident we can make an impact in the real world. And I hope this is one thing that you take away from this, because I think this mindset is a quite powerful tool. So with that, it wraps up my presentation, and I want to thank all the researchers who have contributed to this over the years, as well as our current sponsors and partners on all this work. You can see more about this work at our website, gear.mit.edu, and you're welcome to always ping me at awinter@mit.edu. But I also know why you all came here, which is to see the premiere of this new film by John Freidah, No Drop to Spare, bringing precision agriculture to resource-constrained markets. So what you're going to see now is a huge effort by not only John, but our whole irrigation team globally to really show what we've been able to do with irrigation around the world. It's been an incredible honor to just be part of this and see what John was able to put together. So with that, why don't we dim the lights, and I will get the film ready. Do you want to turn down the lights? Oh, he's got it. Great. If you look around the world, agriculture is the biggest employer. And the majority of those farmers are small-scale farmers in water-stressed countries where people also often do not have grid electricity access. The most powerful means of helping them rise out of poverty is irrigation, because they can grow more and higher value crops and make more money. Challenge is that already 70% of fresh water in the world is used for irrigation. So we have to think, how can we enable these farmers to benefit from irrigation, but do it in a way that is compatible in terms of water use and in terms of economic constraints for where they live.
Water share per capita has declined. Most of our groundwater resources have been depleted. Jordan faces this great challenge of being able to produce food with less amounts of water. We live at a time where agriculture needs to be precise.
There are countries in this region who are 50 to up to 90% dependent on imports. And food security is really linked with national security here. What we are looking at is this nexus between water, energy, and food. And that's where this MIT solution comes into play.
We wanted to provide the benefits of precision agriculture in historically non-precise environments. And the way we did that was realizing that we could put a lot of the computation power for an irrigation system, deciding how to use energy and how much water to move day by day. We could put those capabilities up in the cloud. And then we could just send commands down to the field, and in many cases received by a farmer's smartphone.
Tomorrow when the schedule is going.
To say when to turn on different parts of the system in order to maximize your usage of energy and minimize your wastage of water.
good. Thank you. Bye. We've talked to over 100 farmers, and we found that they're really interested in solar power. So what we're trying to do is optimize various components of the system to make sure that that cost is as low as possible.
We're running this field pilot in Kenya, Morocco, and Jordan because these are all great candidate markets for eventual adoption of our technology, but for different reasons. In Kenya, we've seen that there's a large opportunity for growth of smart irrigation, particularly in smaller scale to medium scale farms. Precise irrigation or smart irrigation really hasn't been adopted. In the Middle East and North Africa, you have a lot of water stress. We're testing in Jordan a system that's still manually operated by the farmhand, where they're getting smartphone commands, and running a drip irrigation system with solar power. And then in Morocco, we're running that technology, but with automation, because we're running on a bigger farm that has the capability where the system can automatically turn on and off different parts of the field.
The objective of this project is to reduce the upfront and ongoing cost of drip irrigation, particularly off-grid drip irrigation.
People usually understand their own problems really well, and they're very good at coming up with solutions to them.
These farmers are very smart, they're very intuitive, they're very resourceful.
And so as designers, our role really is to provide a different set of expertise and another avenue for them to get the tools or the resources that they need.
Drip irrigation works by using a network of pipes throughout the farm and delivering water directly to the root of the crops, and that helps save water.
Typically, drip irrigation is promoted as a water-saving technology, but this is really only the case if farmers are operating the drip system correctly. And this is the purpose of introducing a controller that can help the end user properly irrigate without risking the livelihood of the farmer, but ensure that they're still gaining the benefits of drip irrigation.
The controller takes in weather information, relative humidity, temperature, irradiance, wind speed values, as well as precipitation. And using AI, it calculates and predicts what the solar irradiance profile is over the day, as well as what is the exact irrigation needs for the farmer. It can also use extra energy and store it in a battery for later times of low solar irradiance. Different countries will have different soil types, different crop types, they'll have a different layout on their farm, and all of this can be incorporated into the controller to make it flexible and specific to that farm.
It's crazy to me to think about what a normal PhD experiment looks like. We're all the way across the world, we're on a real farm, and this is a big, like hectare scale farm setup. So to see all this come together, to see the technology, see the solar panels, weather station, the controller in the pump house, and this size of farm that we can irrigate is amazing. The way this technology works is that we're always tuning the water delivered to the plants given their needs. I think a unique facet of how we've approached this research is that we've concurrently advanced the technology of these smart irrigation systems while also learning about end users' needs and their requirements and the value propositions that would drive them to adopt the technology.
Our group is very good at creating design theories and optimization theories to be able to understand complex trade-offs. But the thing that really gets us there is doing frequent field work with stakeholders. It's not just that it has to be good for the farmers, it has to be good for the people that are going to make it run every day, and it has to be good for the people that are going to sell it, and it has to be good for the people who are going to make policy around it. So we have to align all of those interests.
The MIT Gear Lab has logically thought through the steps and been engaged with farmers to see what they need and how they would apply this technology.
And it also is
What was most impressive today is how eager farmers wanted to have access to these technologies. So the questions about when will this be ready for us to purchase? What is the cost of this technology versus that?
I'm a farmer. I want to change my mortality to a new one. So I come here to learn. I think it will help me in my farm.
Everybody's so friendly and so helping and really just wants to see this become a real product and help people in their countries. So I'm just so grateful for all the people that I've worked with. I think that's the thing that I'll remember most.
So I think we have all the building blocks that we need to cover this last mile. We are almost there. We have a private sector partner, we have the institutional partner, and we have the research and R&D partners with us. So I think together we complete the bigger picture.
It's an incredible opportunity for a scalable outcome to research.
We're always trying to design systems that will integrate into ecosystems. We have a lot of control about how we design the system, but the ecosystem is there and we have minimal influence over it. So we have to adapt to it while we innovate for it. Because it's so easy to innovate something that's novel but worthless. If we want to make a real world impact, the only way to do that is boots on the ground. Because there's no way me in a lab in Cambridge, Massachusetts understands what life is like for a farmer in Kenya. Freidah. And I'm happy to take your questions. Thanks for sticking around till 4:30.
All right, looking for hands. I'll get the ball rolling. I guess whether it's electrodialysis or reverse osmosis, these methods are going to generate some highly saline brines.
Yeah.
So what's the plan? What will happen to those?
It all depends on the context. So, in a place like Texas, the regulatory standards are different than a place like California. And so Texas already uses deep well injection because there's very salty aquifers that are actually more salty than the brine. Texas is also close to the Gulf, so surface discharge is used commonly. The de facto solution is an evaporation pond, which you set up and evaporate the remaining water and collect the salt as a waste, solid waste. And I didn't report this in any cost figures, but that evaporation pond cost can often double your levelized cost of water. So the fact that we produce much less brine because the system runs more efficiently than RO as far as recovery means that we need a smaller pond. And so that's an additional cost advantage that ED has over RO at small scale.
Great, thanks. Okay, but I think they're making.
Thanks for coming, Colin.
Oh, okay.
Good to see you, man.
So any cost benefits that the farmers that you're working with generate from using your drip irrigation system, have they spoken about what they can do with it? Like, can they purchase land with it? Is it available to them to purchase more land to create more crops?
That's a good question. I don't. We haven't ever asked them what they would do with money saved, so I don't have a great answer for you. The understanding within the global development community is that you just get out of poverty. You can send your kids to school, eat better, have a higher quality of life overall. But I can't pinpoint for you like exactly what they'd invest in. But farmers are entrepreneurial. Absolutely. So one of the interesting things that we saw in Jordan is that a number of farmers had already adopted solar power just because grid energy costs are really high. And so it was worth that investment. And one thing they said to us is that they were less scared of capital cost increases to adopt our system because they could sell land to do it. They just wanted to reduce recurring costs of energy, and that was the big driver for adopting solar.
Cool. Thank you.
Amos, when you're in the field, how much do you geek out about the technology with the people, the farmers in there? Are they getting excited about learning more and getting with you into the details? Or is it more like, I have this problem and you solve it?
No, I think they absolutely, well, I don't think they geek out about technology for technology's sake. They geek out about value to them. Mm-hmm. So, in the Middle East and North Africa, like water stress for farmers, they get a certain allocation. The government basically turns the pipes on or turns the canals on every once in a while, and they get water. So the value proposition of being able to stretch that water further to grow more crops is very compelling to them. We were not sure if they would be keen on using like a smartphone and having this machine up in the cloud tell them when to irrigate. And that's why the field days have been so important, because they've said, well, actually, yes, because I don't exactly know how much to irrigate all the time. So I'd like to get some guidance. And we have to take that feedback in as well, because the other side of that coin is they don't want a machine making all their decisions for their lives. So the farmer can override any of this. Right? And that actually puts them in the loop in another way I didn't talk about, in that they can notify the controller of water stress and say, hey, we actually need more water. So I think we're on the track to finding the right balance of automation and manual.
Very cool, thanks.
Yeah.
Amos, hi. Thank you for putting a great presentation.
Thanks for
together.
coming.
Oh, my pleasure. So we see at the component level what you've done, what your students have worked on. We see at a system. I mean, everything's super impressive. It looks like you've optimized so much in this system. My question is, what's next?
It's funny. I will joke with people often that most of my time is spent aligning value propositions. So I'm always pushing our partners to, for Toro, for example, their ag market is really focused primarily on the US and South America. And they have a European division that services the Middle East and North Africa. But it took a long time for them to really see like the potential of massive market disruption with this. And so that was kind of a long game diplomacy effort. And then, another example is like how USAID is supporting us and actually supporting Toro to scale up production. Because like at first, that conversation is like, what are you talking about? USAID would sponsor a US company? That's bananas. And so that conversation has to be like, well, if you want this to get to the Middle East quickly, that's the avenue to do it. So what's next for me is that just continual pressing on all the partners to keep the value propositions aligned and learn myself how to align them to try to shepherd these technologies to the finish line. And then a direct answer on irrigation, though, is so USAID has invested in this large-scale 3-year program, and agriculture is a very risk-averse industry, right? Because if you lose a crop, you're out of luck, right? So we have to get farmers excited about this technology on a bigger and bigger scale over time. So what will happen over the next 3 years is successive field pilots and more farmer days, which in year 3 will result in probably about 100 different systems around the Middle East and North Africa that farmers can see and interact with. And it'll be at that point where we transition into a company that can scale it to the next step.
Amos, first, amazing talk, and congratulations to you and your group for doing all of this. It's super impressive to see the technology and the partnerships and how it all fits together. Back to your framework, I'm wondering if you can share an example of something that you considered that didn't quite fit the sweet spot, or maybe a project that went to a certain stage and you had to say, this isn't meeting the metrics, so we have to prioritize other things.
Yeah, it happens constantly to us. So an example that comes to mind is that in our early desalination work, we were trying to produce water at WHO targets. So you can drink water under 500 milligrams per liter, fine, it won't hurt you. And even our municipal water is usually a few hundred milligrams per liter. And so we had designed our systems around that, but at the time, we were focusing on India as a beachhead market, and what's happened there over the last 20 years is people have gotten accustomed to RO-treated water. You buy water bottles that are really low salinity, like tens of milligrams per liter, and they've developed a palate to it. And so our commercial partner was like, there's no way we could ever get people to adopt water that tastes differently. They want super low salinity. And how that affects us technologically is that at that time it doubled our energy needed to get that last amount of salt out. So it totally disrupted how we design systems. But then what's cool about that is that constraint that was applied made us innovate other tricks to be able to run a smaller scale ED stack in a way, actually with variable current to the stack. That's where that technology started, in order to basically get more bang for the buck out of the stack, where we cycle batches and we're changing all the time how much current density is going through it. And so the moral of that story is that we very much try to put ourselves in situations to fail early and often and not catastrophically, in order to get that feedback to then iterate within the innovation loop and then go test it again. And so with the stuff you saw today, it's more mature, but all of those systems had different types of failures along the way that then led to innovation. Oh, Warren's got one.
As we fly across the country, we see these water circles.
Yeah, center pivots.
In, say, Kansas.
Yep.
And that aligned with where you said was high stress for the U.S.?
It's a big, the Central Plains has a big brackish aquifer.
So, what's the potential for this work in Kansas?
Yeah, we absolutely. Going back to aligning value propositions from Danny's comment, when we first interacted with Toro, we actually did a market study around the U.S. in areas where there would be good adoption for drip irrigation and potential desalination, like we're talking about now. And so, we'll often have to do those market studies to show the industrial partner, hey, there's this great opportunity here. But yes, the opportunity is large globally for desalinated water for ag. The trick is getting it cheap enough. And then also water rights play into this. Like in the Central Valley of California, it's a big issue because farmers can just kind of take as much as they want. So it'll be interesting to see how those regulatory standards change. But to put this another way, in the last year, I've spent a lot of time at the big water-related conferences like COP27 and UN Water Conference. And what we keep hearing over and over and over by the water ministers of the water-stressed countries is that we need to utilize brackish water, for ag and potable. We need to use renewables to use it. We need better adoption of drip irrigation. And so it's been exciting to see that we're ticking those boxes. So I think our technologies are quite well aligned for not only what's needed right now, but what's going to be needed in the next decades. That was a roundabout answer to your question, but directly, yes, Central Plains have brackish water and you can reduce the salt out of that if you desalinate it. So yes, there is a market there. Yeah.
Thanks. Hey, Amos. Can you talk about the India situation where the water depletion looked so great? If you're using that brackish water, aren't you just going to exasperate that situation by drawing more out and bringing more salinity into the water?
Well, not, at the limits, sure, right? But right now it's an underutilized water source. So what it would do is take stress off freshwater sources and allow them to be replenished, more easily. Because India's, about at the point, I think on average of the country that their consumption rate is matching about their replenishment rate. And so different parts of the country, their water tables are going down. So the trick with brackish is that it gives you another water source that works even, as far inland as you want to go. Well, yeah.
How are we doing on time?
We're late. But thank you, everybody, for staying late.
Thanks so much.
Appreciate it.
Thanks.
Thank you, Dan. I'm a little sick. How about, yeah.